Swayam Prabha. Digital India. Educated India.
So in the previous lecture, we discussed the different types of end plate connections, rigid connections, a variety of rigid connections, which is known as end plate connections, and then also we solved one example on how to design an end plate connection. In this lecture, we will discuss another variety of rigid connections, which involves welding of the beam flange directly to the column. So these are typically known as welded flange or cover plate type of connections. So here some of the examples are shown of such connections. I'll elaborate a bit. So this is basically a column that is supporting two beams, one on either side, and this is the top view of the same connection. Here you might see that the web of the beam is welded to the column. Also the flanges are groove welded to the column. So the web here is fillet welded to the column and the flanges are groove welded. Now a couple of things you might notice is that the top side there is a bevel in each flange which is groove welded to the column. In this particular diagram, you do not see any continuity plates or any horizontal stiffeners in the column, but sometimes that may also be required depending on the local stresses that we are introducing in the column web and also what is the requirement of shear stresses in the column web. One more detail that could be of interest to us is that it is not necessary to weld the web of the beam to the column. So even though we are welding the flanges to the column, the web could be also bolted because the mechanism of force transfer for the two types of part or for the two parts of this connection are quite different, and therefore it is possible to mix welds with bolts because bolts will be primarily designed to resist the shear force and these welds will be designed only to resist the bending moment. In all these joints, you might also notice this access hole that has been provided. We will talk about that in a minute. Okay. The other example here, some continuity plates could be provided, some stiffeners could be required. And in another example here, what you see is a very different type of a connection where the top flange of the beam is not directly welded to the column, but there is another plate which is used and which is actually slanted plates with a reduced cross-section thickness, and that is welded to the beam, and then other end of the plate is welded to the column, and in addition to that separate arrangements are made to transfer the shear force. So in this particular case both a shear plate as well as an angle seat is provided. So in this lecture we will discuss the force transfer mechanism and design considerations for these types of connections, and then we will do one example. So here you can see in this diagram a typical rigid connection wherein the beam flanges are directly welded to the column. So as we have discussed, the beam flanges are groove welded and they are meant to transfer the design moment capacity, moment demands. And the shear force is transferred through the web. So the web could be welded to the column, but also it is quite common to bolt it to the column. So typically what we do is the column and this shear tab or shear angle or any alternative shear connecting element would be shop welded to the column, and then the column would be brought to the site with this component welded to it, and then the beam is also brought to the site wherein all these geometrical features have been added at the shop and brought to the site. Then at the site, first the beam is aligned with this with these holes, and then these bolts are placed. So these bolts also not only resist shear, they also act as support during the erection process. Once these bolts are in place, then this beam is stable. Then welders can get there and they can weld, they can provide a site weld between the beam flange and the column flange. Okay. So since in this connection the beam is directly welded to the column instead of an intermediate end plate like what we saw in the previous case, because of that this connection is more rigid in comparison to an end plate connection typically. So as I mentioned just now, this weld, which is the groove weld, it's a site weld. So generally site welds are to be avoided, but in this type of a connection, site weld cannot be avoided, and appropriate provisions should be made for proper inspection and quality control for any site weld, in addition to increasing the factor of safety that we use for a welded connection. So here you might notice that only the top faces of the flange should be beveled. Why the top face? Because that is where the welder can easily access and easily deposit the welded material, the welding material. If it was beveled from the bottom, it would be very difficult to weld upside down. Okay, because it's a site weld, we cannot rotate the column upside down. It has to be welded in this configuration only. So it is better to bevel them in the same direction. So that sign is shown here, representing the bevel in the bevel groove in the column in the beam flange. And typically such welds are complete joint penetration welds. Complete joint penetration weld is critical because it provides it the required level of ductility, which is usually missing in a partial joint penetration weld. When we pull this flange apart from this flange, if it's a partial joint penetration weld and there is no other component resisting opening of the root, a PJP type of a weld would perform very poorly under this situation. Therefore, in such situations, complete joint penetration is very critical. Access holes are also required at both sides. So here obviously we require the access hole so that we can reach the full penetration. So because of the presence of the web, it is very difficult to take the electrode all the way from one side to the other side. The web prevents moving of the weld from this side to other side. Therefore, in order for us to develop a nice groove weld, a continuous weld, we have to cut a small hole so that welder can first weld from this side all the way to the middle and go a little bit over to the other side on the middle, from the middle, and then complete the weld from the other side. Here also an access weld is required because again we need to provide, in addition to in order to be able to provide this weld, sometimes this gap is bit too much and we may have to provide a backing strip or a backing plate. And when we need to provide a backing plate, we also require to cut this portion so that backing plate can be tack welded to the beam. These access holes also play a very important role in separating the moments from shear. So because of the presence of this particular geometry of this access hole, and this geometry is also, if you go to the detailing guidelines, you will see that this geometry is very specific and one needs to satisfy that specific geometrical requirement in order to avoid any stress concentrations in this region. So, but because of the presence of this access hole, any shear force demand does not get transferred to the flange, because if you can imagine, if we move this beam up or down, the flange can very easily deform and would not transfer a lot of shear force to the weld, and most of the shear force will get transferred through these bolted joints. In these connections as well, if the stress concentration, because after the groove weld is done, this will become a monolithic kind of a component, and any axial forces which are acting on these flanges will get transferred to the column flanges and then to the column web, which may introduce local stresses which can cause web crippling and web local buckling, etc. In order to avoid that, we have to put some we may have to provide the stiffeners, and also if the shear capacity is not available, not sufficient, we may provide some kind of a doubler plate or a diagonal stiffener. So now we know the basic philosophy of these connections, how they behave. They are very simple for calculation point of view. The only challenge with these connections is that they require a site welding, which is very critical for the performance of the connection. But these are one of the very common types of connections, especially when it comes to moment resisting frames. So in this example, the beam dimensions are given ISMB 400. The different useful parameters such as the thickness of the flange, The width of the flange and thickness of the web are also mentioned here. The column is an ISHB 300 section. So column, of course, is not as deep as the beam, but it is wider than the beam. So column's width is 250 millimeters as compared to the width of the beam, which is only 140 millimeters. Then there is a shear tab that has been provided. Shear tab is just a plate, which is a 10 millimeter thick plate of dimensions 225 in the vertical direction and 125 millimeters in the horizontal direction. And then appropriate bolts are provided. So 3 bolts of 22 millimeter diameter and 8.8 grade are snug tightened in these locations. The force demands are given as the shear force demand is 300 kilonewton and the factored moment demand is given as 125 kilonewton meter. So there is a vertical force in this direction which is 300 kilonewton and there is a moment of 125 kilonewton meter. So we will go one component at a time. First we will check the strength of the bolt, then we will check the strength of the weld which is provided between the shear plate and the flange of the column. We are assuming here that the shear plate is safe for this force demand. One may check, however, whether it is sufficient or not. In this calculation, we will not check the strength of the shear plate. And then subsequently, we will check, will design the welds here and here. So since these are complete penetration joint welds, we already know the dimensions. All we can do is we can check whether they are sufficient or not. So we will start with the bolt strength. There are total 3 bolts. There are 3 bearing surfaces between the bolt and the beam web, and there are 3 bearing surfaces between the bolt and the shear plate. Now the shear plate thickness is given as 10 millimeters, but the thickness of the web of the beam was only 8.9 millimeters. And we are assuming here that all these sections are made of Fe 410 type of steel. So its yield stress is 250 MPa and the ultimate stress is 410 MPa. The bolts are 8.8 grade bolts. So for the design of the bolts, let's first assume that the pitch and the end distances are sufficient that they don't start to control the strength of the bolt. So first let's look at the bearing strength of one bolt. So bearing strength for one bolt is given by 2.5 times dt fu kb. I hope you remember what these parameters represent, divided by gamma mb. Gamma mb is the factor of safety. Now fu was the ultimate strength of the bolt, and the kb factor controlled the effects of the pitch versus if the bolt is of a weaker bolt is stronger than the plate, then we would use the fu of the plate. The d is the diameter of the bolt and t is the thickness of the plate that we are designing for. So since the thickness of the web of the beam is smaller than the thickness of the shear plate, so we will use tw of the beam. Since there are 3 bolts, we will multiply the same values with 3. So 3 multiplied by 2.5 multiplied by the diameter of the bolt multiplied by the thickness of the web multiplied by the fu of the beam web divided by a factor of safety of 1.25, and we get the bearing capacity of 3 bolts as 482 kilonewton. Shear strength of the bolt. So the bolt itself can undergo shearing type of a failure. We need to check for that. The shear strength, again, I hope you remember where it comes from, is given by ANFU, assuming that the shear plane passes through the threaded portion of the bolt. That is a conservative assumption. ANFU divided by root 3 divided by gamma MB and multiplied by 3 bolts. So 3. So area of cross-section area of a bolt can be taken as pi r squared. R is 11 millimeters. 11 millimeters multiplied by 0.78. So 0.78 basically is the factor that we can multiply the gross cross-section of the shank to calculate the net cross-section of the threaded portion, multiplied by fu by root 3 divided by 1.25. So here fu for this bolt is 800 MPa. So 800 MPa divided by root 3 will give us 462 divided by 1.25, and we get the shear strength of the bolt as 328 kilonewton. Now the demand for the factored shear force demand was given as 300 kilonewton. the shear strength of this bolted joint is more than 300. It's actually 328, so it is safe. So now let us check the strength of this weld that is connecting this shear tab with the column flange. So as we can see, there are two welds, one on each side of the shear tab. The size of the weld is marked as 6 millimeters. So the strength of this weld can be calculated easily. We know the expression for the strength of a fillet weld. We use Fu divided by root 3 as the material strength, because we assume that the strength of such a weld is governed by shear strength. That is as per the Indian Standard Code IS 800. Lw is the length of the weld multiplied by the throat thickness. So this gives Lw multiplied by throat thickness gives us the effective cross section area divided by gamma mw. That is the factor of safety. Factor of safety in this particular case, we will take it because this will be a shop welded connection at this location, and this weld will be site welded, but this is a shop welded connection. Therefore, we can take gamma mw as 1.25. Okay, so we substitute the values. Fu ultimate stress for the parent metal is 410 MPa. Length of the weld. So since the plate depth or the plate length is 225 millimeters, we will leave some at the ends. We should terminate slightly short of that edge. Therefore, I'm leaving 3 times the weld size at each end, and that is the actual length that is available, multiplied by a by root 2, that is the weld size, divided by root 2, and the factor of safety. And we can calculate this strength to be 333 kilonewton, and the shear force demand was given as 300 kilonewton. So the shear strength of this joint is more than the shear demand. Therefore, this weld is also safe. So now we have checked the safety of these bolts and safety of this weld. Now let's check the safety of these welds that are between the beam flange and the column flange for the given bending moment demands. Now these welds, of course, they are given as complete joint penetration welds, and they are done on both flanges. So the thickness of the weld or the throat size of this weld will be 16 millimeters. That is the thickness of the flange of the beam. So we will use 16 millimeters as the throat size, and using that we can calculate the capacity of this weld under tension. So now let us calculate the strength of these welds under this type of loading, wherein this flange undergoes tension. So as we know, groove welds are basically treated same as the parent metal, and the failure is governed by the yield strength. So we will use the yield strength value Fy, and the throat thickness, that is A, multiplied by Lw. So A would be 16 millimeters, Lw would be the length of the weld, which is nothing but which is same as the width of the flange. So we will take that as 140 millimeters divided by the factor of safety, partial factor of safety. In this case, since this is a field weld, this symbol also represents that this is a field weld. Therefore, gamma mw will be equal to 1.5, and we substitute these values and we get the weld strength as 373 kilonewton. Now, for a weld of this strength, how much moment can it resist? Since there are welds present at both ends, we can calculate the moment capacity of this weld couple by multiplying this strength with the lever arm. So lever arm between the two welds can be estimated as 400 millimeters, which is the depth of the beam. To be more precise, we could have taken it as the distance between the flange center to the flange center, but here it is done rather approximately, and this strength turns out to be 149 kilonewton meter. The demand for factored bending moment demand was 125 kilonewton meter, and the capacity is 149, which is significantly higher than the demand, and therefore this connection can be considered as safe. So we have checked the safety of the bolts, the safety of the weld between the shear tab and the column, and the safety of the welds between the beam flanges and the column. Now the remaining aspect of this connection would be to check the safety of this portion of the column. Now again, we will not discuss that part in this course. This will be should be covered separately in a plate girder section, because it is more relevant there. So if you want to study that part in more detail, please go ahead and read those sections in the Indian Standard Code and in the textbook. So this concludes the discussion on non-ductile frame connections. Subsequently, we will talk about the ductile frame connections for earthquake loading conditions.